Good day, my dear listeners, my dear students. Today, we are going to look at indices. And we begin with the laws of indices. Indices, the plural of index. Index, the plural of index is indices. Indices. Now, if A is a number and M and N are positive or negative integers or fractions, then 1. A raised to the power M multiplied by A raised to the power N is equal to A raised to the power M plus N. Example is 2 raised to the power 3 multiplied by 2 raised to the power 2 is equal to 2 raised to the power 3 plus 2, which is 2 to the power 5. Number 2, A raised to the power M divided by A raised to the power N is equal to A raised to the power M minus N. Example, 2 raised to the power 5 divided by 2 raised to the power 2 is equal to 2 raised to the power 5 minus 2, which is equal to 2 raised to the power 3. Number 3, A raised to the power M in bracket raised to the power N is equal to A raised to the power Mn and multiplied by N. Example, 2 raised to the power 3 in bracket raised to the power 2 is equal to 2 raised to the power 3 times 2, which is 2 raised to the power 6. Number 4, A raised to the power minus N is equal to 1 over A raised to the power N. Example, 3 raised to the power minus 2 is equal to 1 over 3 raised to the power 2, which is equal to 1 over 9. Number 5, A raised to the power 0 is equal to 1, provided A is not equal to 0. That law is very interesting. This proviso is telling you that you cannot raise 0 to the power 0 and get something. It's not possible for man. Raising 0 to power 0 to get something, to get 1. But interestingly, any number outside 0 raised to the power 0 is equal to 1. Which means that 1 million, if you raise 1 million to power 0, it is equal to 1. If you raise 1 billion to power 0, it is equal to 1. If you raise 99 to power 0, it is equal to 1. Any number except 0, the reason is obvious. There's no way you can raise nothing to power nothing and get something. Are you God? So take note of that law. A number which is not 0 raised to power 0 is equal to 1. Then number 6, A raised to the power 1 over N is the same thing as the nth root of A. For example, 8 raised to the power 1/3 is equal to the cube root of 8, which is equal to 2. And number 7, A raised to the power M over N. A raised to the power M over N is the same thing as the nth root of A raised to the power M, or the nth root of A in bracket raised to the power M. Excuse me. Example, 8 raised to the power 2 over 3 is the same thing as the cube root of 8 raised to the power 2, or the cube root of 8 in bracket raised to the power 2. Now, if you look at this last example, you will see that these two interpretations are quite long. They are in order. They are in order. Why? 8 raised to the power 2 is equal to 64. And the cube root of 64 is 4. The cube root of 8 is 2. And 2 raised to the power 2 is 4. So you can see that they are the same. So that interpretation is very much in order. And these are the 7 laws of indices. Now, you will take note. You will take note that if you have something like this, n to the power n, this n is the index of this. N to the power n is a number in is the power of n. Now n is the index. N is the index. If you have a number like a 2 raised to the power 3, 3 is the index. 2 is the base, the number that you raise to the power 3. 3 is the index. And like I told you, the plural of index is indices. Index. Indices. Index, singular. Indices, plural. Now, having given you examples for each of these laws, I don't need to give further examples. But I'm going ahead now to take you a bit further in what we call simple exponential equations. Simple exponential equations. So, these are the 7 laws of indices which we can easily apply to problems from now. We are going to what we call simple exponential equations. Simple exponential equations. They usually arise from the laws of indices. Now, simple exponential equations. Simple exponential equations. An equation of the form ax is equal to b, where a and b, where a and b are numbers. And x is a variable. It's called exponential equation. Notice that the variable is used as index or exponent the variable is used as index or exponent. It is the variable that is used as index or exponent. It is very important. Before you can call an equation an exponential equation, the index or exponent must be the variable in the equation. Now, let us solve the equation. Let us solve the exponential equation. The equation 2 to the power x is equal to 8. Please take note of this equation. 2 to the power x is equal to 8. Is an exponential equation. Like I have already said, the index or the exponent is the variable. So x is the variable in this equation. X is the variable. X is the variable. X in this equation is the index of this base. Index or exponent. We are trying to solve this. This is an equation. This is a simple exponential equation. We have to solve it. How do you solve it? Two raised to the power x is equal to 8. That is what we are given. But we know that 8 can be written as 2 to the power 3. 2 to the power x is equal to 2 to the power 3. What do you observe on both sides of the equality sign? 2 raised to the power x is equal to 2 raised to the power 3. That can only happen when the indices are equal. As long as the base is the same on both sides, 2 raised to the power x is equal to 2 raised to the power 3, the same 2. That can only happen when the indices are equal. Please take note. And so, if 2 to the power x is equal to 2 to the power 3, then x is equal to 3. That is, x is equal to 3. Yes. Yes. You want to check? Okay. If x is 3, then replace this x here with 3. 2 to the power 3 is 2 to the power 3 must be equal to 2 to the power 3. There's no argument about that. This is an example of a simple exponential equation. So, what we are saying here, when you get to this stage, you see the argument we made there. Now that both sides of the equation 2 to the power x is equal to 2 to the power 3, both sides of the equation are on the same base 2. We proceed to equate the indices. 2 to the power x is equal to 2 to the power 3. That can only happen when x is equal to 3. So, I'll give you the side note that notice that both sides of the equation are on the same base, on the same base, that is 2. Therefore, we proceed to equate the indices. That is x is equal to 3. That is precisely what we did here. As soon as we establish the same base, both sides of the equations being on the same base, our next step is to equate the indices. Now, let me give you some further examples so that you will understand very well how to solve simple exponential equations. I want to give you more examples. Let me give you more examples. What examples? Solve each of the following equations. One half to power x is equal to 8. 2, 3 into 3 to power x is equal to 27. 3, 0.25 raised to power x plus 1 is equal to 16. 4, 3 raised to power x is equal to 1/81. And 5, 10 raised to power minus x is equal to 0.1234, 12345. Number 6. Number 6. 2 raised to power x plus y is equal to 4, and 3 raised to power x minus y is equal to 81. I think I have to stop at this number. I'm sure by the time we attend to these equations, you will understand very well how to solve simple exponential equations. So let us go to the solutions. Solutions. The first one that is half to power x is equal to 8. We should always aim at putting both sides of the equation on the same base. That should be your aim. To get both sides of the equation on the same base. Because once they are on the same base, you equate the indices. That is the rule. So you have to make all efforts to see that both sides of the equation are on the same base. On the same base. Now let us proceed. Half to the power x. Don't forget your laws of indices. Half is the same thing as 2 to the power minus 1. Please take note. The power x is equal to, let us just go straight on. And right is equal to 2 to the power 3. Please take note. 2 to the power minus 1 is the same thing as half from our law of indices. So this again attracts one of the laws of indices to become 2 to the power minus x. What do you get minus x? Minus 1 multiplied by x will give you minus x. What do you observe now? You observe that the two sides of the equation are on the same base. The two sides of the equation are on the same base, 2, 2. And so what now do we do next? We equate the indices. That is, minus x is equal to 3. Yes. Giving us what? Therefore, x is equal to minus 3. I hope you understand that. That is what it should be. If you exchange the sides, you get that x is equal to minus 3. And one thing is obvious. Whenever you solve an equation, you can check. You don't need to ask somebody what the answer is. You don't even need to go to the answer pages in the book. You can check your answer. You can check it by yourself to know whether it is right or wrong. Now, what do we do? If x is equal to minus 3, if x is equal to minus 3, bring it up here. That is 2 to the power minus x is equal to 2 to the power minus 3. If x is equal to minus 3, then it means that 2 to the power minus x is equal to 2 to the power minus 3. Minus 3 becomes plus 3. Which means 2 to the power 3 plus 3 is equal to 2 to the power plus 3. Is there any argument about that? No argument. Now, number 2. Number 2. 3 into 3 all to the power x is equal to 27. Remember what I said about our objective. Our objective is to ensure that both sides of the equation are on the same base. On the same base. Now, what do you observe here? Very clearly, 3 to the power x is equal to 27 over 3, which is what? 9. Which is 9. We begin with that. For example, that is, divide both sides of the equation by 3. 3 to the power x is equal to 9. And 9 is 3 raised to the power 2. That is 3 raised to the power x is equal to 3 raised to the power 2. We have achieved our objective. Both sides of the equation are now on the same base. The same base 3. What happens? The indices must be equal. That is x is equal to 2. And of course, we can check our answer again. Like I said, we can check. You don't need to ask anybody whether you are right or wrong. You check it yourself. How do you check? If x is equal to 2, replace this x with a 2. 3 raised to the power 2. Is it not 9? It is 9. And 9 multiplied by 3. Is it not equal to 27? There you are. So you can check. You can check your answer. You can check it to know whether it is right or wrong. You don't need to ask anybody. Now number 3. Number 3. Number 3. Number 3 is 0.25 to power x plus 1 is equal to 16. 0.25 raised to power x plus 1 is equal to 16. What is 0.25? 0.25. Is it not the same thing as 1 over 8? Check well. 1 over 8. Check well. 1 over 8 is equal to what? One over 8 is equal to what? Okay, now. Okay. What is one quarter? Let us take 1 quarter. 1 quarter. 1 quarter. 1 over 4. If you convert 1 over 4 to a decimal number, you will get 0.25. 1 over 4. You will get 0.25. So this thing is the same thing as 1 over 4 raised to power x plus 1 is equal to 16. And 1 over 4, is it not the same thing as 4 to power minus 1 from our laws of indices? This gives you 4 to power minus 1 to power x plus 1 is equal to 4 raised to power 2. I want you to observe that very well. Notice that our objective remains ensuring that both sides of the equation are on the same base. So 1 over 4 is something as 4 to the power minus 1 from your law of indices. You see how that power there, or index there? 16 is the same thing as 4 raised to the power 2. Now, here again, by applying one of the laws of indices, this thing is equal to 4 raised to the power minus x minus 1 is equal to 4 raised to the power 2. Please don't be confused here. When you multiply plus x plus 1 by minus 1, because you have to multiply the indices. It's one of the laws of the indices. When you have a raised to the power m in bracket raised to the power n is equal to a raised to the power mn, n multiplied by n. So here, this is going to be minus 1 multiplied by x plus 1, which becomes minus s minus 1. That is what you will get. But what happens now? Both sides of the equation are on the same base, 4. Yes, they are on the same base, 4. What follows next? You equate the indices. That is, and I'm saying that minus x minus 1 is equal to 2. Oh yes. Minus x minus 1 is equal to 2. And of course, that is a simple equation now. Which gives you x is equal to what? X is equal to minus 3. You should know how we got minus 3. How do we get minus 3? When you carry minus x to the other side, it becomes plus x. Carry plus 2 to the other side, it becomes minus 2. Minus 1 minus 2 is minus 3. So x is equal to minus. Do I need to ask anybody whether I am right? Or I go back to the given equation now and check. If x is equal to minus 3, let me check. Let me check. Let me check. X is equal to minus 3. Now, watch it very carefully. Bring it here. Bring it to this line. If x is equal to minus 3, then minus x becomes minus 3, which becomes plus 3. Plus 3 minus 1 is 2. Which means you have 4 raised to the power 2 is equal to 4 raised to the power 2. Is there any falsehood in that? It is true. So, like I advised you, don't ask anybody whether you are right or wrong. Check your value by yourself. You should check it. Go back to the equation and check. If you are right, you will know. If you are wrong, you will know. Now, number 4. A to power x is equal to 1 over 81. Remember our objective, to place both sides of the equation on the same base. 3 to power x is equal to 1 over 81 is the same thing as 3 to power 4. 3 raised to power 4. That is 3 times 3, 9 times 3, 27 times 3, 81. So 81 is the same thing as 3 raised to power 4. So instead of writing 1 over 81, I'm now writing 1 over 3 raised to power 4. And then from our law of indices, 3 to the power x is now equal to 3 raised to the power minus 4. From our law of indices. What happens? They are on both sides of the equation are on the same base, 3. So x is equal to minus 4. X is equal to minus 4. You can check whether you are right or wrong. Now, question number 5. 10 to the power minus x is equal to 0.000001. That is 5 zeros. You convert this decimal number to power of 10. Convert it to power of 10. And you will get 10 to the power minus x is equal to 10 to what power? I think it should be minus 5. Or is it minus 6? I think it should be minus 6. Check whether it should be minus 6. You check it. Check it. 0.000001. Is it the same thing as 10 to the power minus 6? Don't forget that 0.1. 0.1 is the same thing as 1 over 10. 0.01. It is the same thing as 1 over 10 to the power 2. Yes. 0.001 is equal to 1 over 10 to the power 3. 0.0001 is equal to 1 over 10 to the power 4. Take note, when you have no zero, it is 10. 1 0, 10 to the power 2. 2 zeros, 10 to the power 3. 3 zeros, 10 to the power 4. So if you have 5 zeros, what will you get? 10 to the power 6. 10 to the power 6. 0.000012345 will therefore be equal to 10 to the power 6. Yes. 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 From what we have seen here, this is equal to this. You have 1, 2, 3, 4, 5 zeros. So this one will be 10 to the power 6. 1, 2, 3, 10 to the power 4, 1, 2, 10 to the power 3, and so on and so forth. So this is correct. What happens? Both sides of the equation are on the same base, 10. Therefore, minus x is equal to minus 6. Is it not the same thing as saying that x is equal to 6? X is equal to 6. X is equal to 6. What's our number 6? Very quickly, our number 6. Our number 6, if you look at that number 6 very closely, you will see that it is going to lead us to simultaneous equations. That number 6 will lead us, because that case we are looking for x and y, and we are given two equations that will help us to raise two simultaneous equations. Now, very quickly, we look at I want to use it to conclude the examples. Very quickly, that number 6 is telling us that 2 to the power x plus y is equal to 4, and 3 to the power x minus y is equal to 81. Like I said, 2 to the power x plus y is equal to 4. From there, we get 2 to the power x plus y is equal to 2 to the power 2. Again, they are now on the same basis. That is, we are saying that x plus y is equal to 2. Call it equation 1. Now, 3 to the power x minus y is equal to 81. 3 to the power x minus y is equal to 3 to the power 4. Because 81 is something at 3 to the power 4. On the same base again. That is, you are saying that x minus y is equal to 4. Call it equation 2. We now solve equations 1 and 2 as simultaneous equations. What happens? Add 1 and 2. Equation 1 plus equation 2. Please take note. Equation 1 plus equation 2. Plus y minus y. Y is gone. X plus x will give us 2x. Now equal to 2 plus 4, which is 6. That is, x is equal to 6 over 2. which is equal to 3. Now, if x is equal to 3, we can substitute for x in any of the equations. Substitute for x. Substitute for x in equation 1. That is, go to equation 1, where you see x, put 3 there. You will now get 3 plus y is equal to 2. Please take note. 3 plus y. That is, instead of writing x plus y, we are now writing 3 plus y is equal to 2. What is y equal to? That is, y is equal to 2 minus 3. And what is it equal to? Minus 1. 2 minus 3 is minus 1. So, when x is equal to 3, y is equal to 2. Again, you can check by going back to the equations, replacing x by 3, y by minus 1, to see whether you are going to get the same thing on both sides of the equation. And this is where we are concluding our work on indices and simple exponential equations. May God bless all of you in Jesus' name. In our next meeting, we are going to look at logarithms, theory of logarithms, and logarithmic equations. Theory of logarithms and logarithmic equations. May God bless all of you.